In the previous chapter, we looked at multivariate functions and derivatives of multivariate functions. In this chapter, we're going to look at integrals for multivariate functions. And as usual, before we get to the multiple variable case, let's remember the single variable case. Okay, so the single variable case, the idea was we have some function f of x. We are interested in the integral from some x equals a to some value x equals b of f of x. Okay, so maybe this is a and this is b. And the integral will give us the area under the curve. And when we got down to it, the way we defined this was in terms of Riemann sums. We approximated the area under the curve by lots of rectangles. By finding the areas of all these rectangles, we could approximate the area, right? So we think about this as a Riemann sum. We have, however many rectangles, n rectangles, and we need the base times the height of each rectangle. So the height would be the sum function value of the ith rectangle. Right? So the idea was you'd pick some x value right here. You plug it into the function, it will tell you the height. Right? And the next rectangle, maybe it's right here. You pick the x value here, plug it into the function, it gives you the height. And then multiply it by the base of the rectangle. Area of a rectangle is just base times height. So this will give us the height or the area of every rectangle. And then you add all those areas together. If you take more and more rectangles, if you look at the limit as the number of rectangles goes to infinity, then this is the integral, right? This is how we define the integral. Okay? So that's a single variable case. Let's look at the multivariable case now. All right? And before I get the picture here, let's kind of describe what we're dealing with. So multivariable case. Okay, so let's limit ourselves to a variable, or to a function of two variables. Okay, we want to integrate, instead of just from a to b, we're going to integrate over some region R in the xy plane. Notice it's a double integral now because we have two variables. Okay, and we have a few ways to represent this at the end. I'm going to use dA. dA means we're going to integrate over area, okay, because this region in the xy plane represents an area. So what do we even mean by this? Okay. So now let's take a look at the picture. We have some function here. In this case, it's paraboloid. Okay. And the idea here is that we're limiting ourselves to some region. Okay, some region R. So here we've limited ourselves to some region R. So that region is what this symbol represents. This is the region over which we integrate. So R is the region in the xy plane over which f is integrated. Okay. And we want the volume over that region and under the surface. Okay. Instead of looking at area, now we're looking for the volume. So this is going to be the volume under the function over this particular region. Okay. So that is what the double integral means in this case. That is what we want to be able to find. So how do we go about finding something like this? Okay, well, we could approach this much the same way that we approach in the single variable case. In the single variable case, we used a Riemann sum and used lots of little rectangles. In this, we can do something similar, but because we're dealing with 3 dimensions, we're dealing with volumes, we have to use not rectangles, but rectangular prisms. We can approximate the volume with lots of little blocks, okay? Just like in the single variable case, the more blocks we have, the better our approximation. So you can see at this point, we have a pretty decent approximation of the volume once we put all those blocks together. So what we want to do is we want to find the volume of all these blocks. We want to add them together, and then we'd want to see what happens as the number of blocks goes to infinity, because that should equal to our double integral. Okay, so that's our strategy. So let's start by just kind of understanding the formula for one of these blocks. So if I have some surface, and I have just one block that I'm using to approximate the volume underneath this surface. Okay, just the one block. Okay. How do we find the volume of this block? So the volume of the block, well, it's going to be length times width times height, right? So I need the size of each dimension. So if we kind of embed this in our 3-dimensional space, then we can think about this right here as being how much the x changes, right? If we go from here to here, we are changing the x value. So that's going to be how much the x changes, the delta x. And then here to here, that's how much we are changing in this amount, in the y direction. So that'll be our delta y. And then, so multiply those together, that gives us our base. And then we need a point to represent the height. Again, doesn't matter which point, some point in here that's going to hit the surface. The idea here is that we pick some xy value, okay? So the x and the y here, we often write this as x star and y star. It means a particular x value, though we're not very picky on which particular x value, and a particular y value. And if we plug that into the function, it will give us our height, an approximation for our height. So f of x star, y star. And again, the only condition for x star and y star here is that it's some x and y that's in the base of this rectangular prism here. Okay, it lives somewhere in the base here. Any x, y that lives there will work and will be a good approximation for the height of the surface. Okay, and so the volume is going to be the height times the length of the base in the x direction times the length of the base in the y direction. Length times width times height. That gives us our volume. Now what we want to do is, that's the volume for one rectangle. we want to find the volume for all the rectangles put together. We want to add them all together. Okay? So what I need to do is I'm actually going to need to add in two directions, right? Because if we look at this, we see that the rectangles go in two directions, right? I have rectangles going in the x direction, I have rectangles going in the y direction. There are two dimensions where I can move here. And so what I'm going to need is I'm going to need two summations. One for the x direction, one for the y direction. So I equals 1 to m. That will add up the rectangles in the x direction. Sorry, not rectangles, the blocks. Let's call them blocks. And this one here, this sum will make it from j equals 1 to n. So there'll be m blocks in the x direction and n blocks in the y direction. This will add up the blocks in the y direction. Okay. The idea here is we're going to do one row at a time. Okay. When we add up the blocks in the x direction, that means for each one of these rows here, might help if I can draw on this. Okay. For each one of the rows here, we're going to add up all the blocks in this row as we go in the x direction. And we turn them all into a single value. And we add up all the blocks in the next row, holding the y fixed. Okay, add them all up, get a single value. So for each row, this inner summation will add up the values in the x direction. And then once I've turned all of this into a single value and all of this into a single value and all of this row into a single value, then we're going to add up in the y direction. So we'll add up all those values and then we'll add them up in this direction, in the y direction. Okay, and so we'll have everything added up by the time we're done. We do one row at a time here, turn that into a single value, and once we have all these in their own little values, okay, we add up this value we get by adding that row to what we got from adding this row to what we got from adding this row, so on. Okay. Now we want to do that for every single block. And we just found the volume of one of the blocks. That's f of x star y star. And let's be a little more specific for the ijth block in the ith row and the jth column. Okay. So this will be a particular x and a particular y that's in the base of the ijth block, the block that's in the ith row and the jth column. Okay. And then delta x, delta y. And as the number of blocks in each direction grows, this summation should get more and more like the integral that we want to find, the volume under the function. So if we take the limit as m and n both go to infinity, let me write it this way. As m goes to infinity and n goes to infinity, then this limit will exactly equal to the integral. Okay? So far so good. We understand that this means the volume underneath the surface. We've translated into this double summation so that we add up everything in each row and then add up all the rows together. Okay. Okay. But this doesn't look particularly easy to calculate, does it? However, if you stare at it long enough, it will look familiar, specifically this bit right here. Okay, if we just focus on this bit right here, what do we notice? That looks a lot like what we had for the single variable function, didn't it? We were adding up just a single summation, some function, and then we had a delta x at the end. And when we had that and took the limit as we went to infinity, we got a single variable integral. Well, that's exactly what we have here, okay? Just looking at the interior here, we have a summation, we have some function, and then we got a delta x. And as we take the limit, that interior becomes a single variable integral, okay? So I'm going to leave the outer summation, but the inner summation is going to become a single variable integral with respect to x. So I'm going to integrate from, say, a to b, f of x, y, j star. We're holding the y fixed, but we're integrating with respect to x. Okay, so we have a single variable integral here. We've dealt with one of our limits, this limit, the m going to infinity. We still have to consider what happens when n goes to infinity. Okay, so hopefully that kind of makes sense. We've broken it down into finding the volume all at once, to breaking it down to going one direction at a time. So we're focusing on just the x direction. Hey, that's a single variable integral. Okay, and now we look at this, and again, it looks familiar. We're taking the limit, there's a single sum, we have something that depends on y, and then we have a delta y. Okay, limit, a single sum, we have something that depends on the variable, and then delta of the variable. It's exactly the formula, the form of a Riemann sum that is equal to a single variable integral. So I'm going to get another single variable integral, but now for y. Okay, so that outer sum becomes the integral from whatever the bounds are, c to d, integral from a to b of f of x, y, sorry, x comma y, dx, dy. Okay? The idea here being these are the bounds of integration for x and for y. And this may not seem like some incredibly deep result, but it kind of is. What we've done is we've taken this integral, which would be an integral to find the volume, okay? Something that this single variable integral on its face doesn't seem like it'd be very good at. And we've broken it down into pieces, so we're dealing with one piece at a time. We deal with this integral first. Okay, we integrate with just respect to x, and we hold y constant. Okay, and then once we're done with that, we do another integral. And now we integrate whatever this result is with respect to variable y from c to d. And so instead of doing it all at once, we're breaking it into pieces, more manageable chunks, integrating one variable at a time. Okay. Now, for now, we're going to just focus on integrating where our region is a rectangle. We will get to a point where the region will not be a rectangle, and then things get a little trickier. But if the region is a rectangle, okay, so for this example, if we're integrating over a rectangle, let me grab a quick screenshot of it. This is region R. I don't have a real good color. This is region R. Okay, that R over which we're integrating in the xy plane. a lot of times we will focus just on the XY plane over the region which we're integrating. In multivariable calculus, that's the tricky part, the region over which we're integrating. Single variable calculus, it's actually taking the integral. In multivariable calculus, the hard part is determining the limits of integration to match the region over which you're integrating. Okay, so in this case, from here to here, that's how far I'm going in my x direction. So I'm going from A to B. Okay, that's the A and that's the B, and I'm integrating with respect to x. Okay, and then y goes from here to here, so integrating from C to D. So the outer integral is integrated with respect to y, and it goes from C to D. Okay. So let's get a little bit more intuition on what's actually happening here. Okay, so let's go back here. So the idea here is we're slicing up this volume that we want to find. Okay, so here I have some example slices. These are only a few of them. There are actually, every way you could slice this thing. But here are a few slices. And the idea here is that I integrate the slices in one direction while holding the other variable fixed. Okay? So you would start by integrating your slices in this direction, right? That would be holding your x value fixed and integrating in the y direction. Notice that's the opposite of what we're doing here. The way I've written it here, we're integrating first with respect to x and then with respect to y. Since the x comes first, we would hold the y fixed. Okay, this picture is drawn a little differently. We would be holding the x fixed. Each slice here, the x value is fixed, and we integrate with respect to y. Each one of these slices, we find the area for each one of these little slices. Okay, area for this slice, area for this slice, area for this slice. That inner integral, that's what it does. So we first integrate here, and then once we've turned all these slices into their own single value, then we integrate the value that we get, okay, with respect to the other variable. So drawing it here, and let me actually take some of that out so you can actually see what I draw. Maybe a little bit more. Okay, so this is the area over which we want to integrate. Okay, the surface is hovering above this. We are looking down from above, down from the down the z-axis. Okay, and we slice it. Each one of these slices, we're integrating. Okay, and this one will match this. We're holding the y fixed. Each one of these slices represents holding the y value fixed. And then if we integrate in this direction over the slice, we integrate in this direction, then we're integrating with respect to x, right? We're adding up each slice in the x direction. Okay, every single little slice here. And integrating each slice, we get a value for each slice. Okay? Let me draw it over here. Okay, once we integrate the x's, it adds all those x's into a single value. Okay, and so we don't have an x-axis anymore. We've reduced the number of axes to just the y-axis. Okay, and so this slice, we added it all up, and it became whatever this value is here. That's that first integration, the inner integral. Okay, so that inner integral here, it does that. It integrates each slice, gives you a single value over here. Okay, and then once you do that, once you integrate that for each slice, then you could add all the slices up. And that's the second integral. Okay, understanding this is going to be really useful for coming sections. The hardest part about these multivariate integral problems is not the integration, it is the limits of integration. And if you understand what we are doing and how this works, it will make finding those limits of integration much easier. Okay, in this particular section, we will be limiting ourselves to rectangular regions. Rectangular regions are much easier to deal with than more general regions, but eventually we will want to integrate over some other region. Okay, maybe something like this, and then we would again have to slice things up. Integrate over the slices. Each slice gives us one value, 1 point on this line, and then integrate in the other direction over the line. Okay, so understanding this going forward is going to be really important. Let's take a look at an example. We want to take the double integral of this function here. We want the integral from -1 to 1, and the integral from -2 to 2. The function we're integrating is 2x plus 3y plus 5. And then we have a dx first. That means we are integrating with respect to x first. The inner integral is with respect to variable x. And then dy second. The order here really matters. Okay? So make sure you pay attention to the order. All right. The evaluation of this is pretty straightforward if you are familiar with integration, if you're comfortable with it. But let's make sure we understand what we're doing before we just go guns blazing to compute this. Okay, so I'm going to sketch the region over which we're integrating. So I'm going to focus on the xy plane. You can imagine us looking down the positive z-axis. Okay, our x's range from -2 to 2. So -2 to 2. And our y, that's the outer integral, ranges from -1 to 1. Okay, which means we are dealing with this rectangular region. This is the region over which we're integrating. We are finding the volume of this function over this rectangle. Okay. This would be equivalent, this integral would be equivalent to us saying we want, this is the double integral over region R, where this region is region R, this rectangle is region R, of 2x plus 3y plus 5, integrated over the area of that region. Okay, that dA means integrated over area. Okay, it means exactly the same thing. Okay, so to actually evaluate this, we'll just evaluate one integral at a time. We start by evaluating the inner integral. Okay, the inner integral is evaluated with respect to x, which means we're going to treat y as a fixed value. Only x is a variable. Okay, so the outer integral, I'm not going to touch yet. That outer integral stays where it is. Okay, but the inner integral, I'm going to integrate with this with respect to x. Integral of 2x is 2x squared over 2. The 2's will cancel, I'll just get an x squared. The integral of 3y, I'm treating y as a constant, so I just get the constant times x. And the integral of 5 is 5x. And I'm going to evaluate that from x equals -2 to x equals 2. Notice the limits of integration here correspond with the variable here. Okay, so x is ranging from -2 to 2 because this integral is on the inside, the dx is on the inside. And then y ranges from -1 to 1 because the integral and the dy are both on the outside. Okay, so let's plug in. So plug in 2 squared plus 3y times 2 plus 5 times 2. Top limit first, and then subtract what I get when I plug in the bottom limit. -2 squared plus 3y times -2 plus 5 times -2. dy. Okay? So if I evaluate that, what am I getting? I'm getting 4, let's do it this way. 4 plus 10 is 14, plus 6y, minus 4 minus 10 is -6, minus 6y. Okay? Notice what we have here now. Notice what variable is missing. There are no more x's. Once you are done plugging in for that inner limit of integration, that inner variable should be gone. It should not be there anymore. And that's what we see here. That inner variable, gone. We only have variable y left over. Only the variables that are here should be in the integrand. Okay? So we could combine like terms a little bit more. 14 minus -6, that's 20. And 6y minus -6y, that's 12y. Okay, so what is it that we've just done? What is it that we've done with this inner limit of integration? Well, what we've done is for every fixed y, we've integrated x. So I'm holding y fixed. Okay, maybe it's this y, whatever that y is, and I add up all the x's. Okay, so at y equals, I don't know, 1/2, right about there. If I integrate with respect to x, I get 20 plus 12 times 1/2. That's what, 20 plus 6, 26. So the area, not volume, the area under the surface along just this one line would have been 26. But I have a formula for that for every slice there is. All right? So it's giving me the area under the surface for every single slice, for every possible choice of y. And so for each slice here, I'm adding up all those x's, turning them into a single value. So I no longer have an x-axis. I added all the x's together. Now I just have the remaining variable left, the y-axis. Okay, because all those x's there, I integrated them, turned them into a single value, and now that single value is right here. Okay, now what I want to do is I want to add up all those individual values so I can get the total volume. Okay, so now I'm doing the other integral. So now I'm integrating with respect to y. I have integral of 20 is 20y. Integral of 12y is 12y squared over 2. I reduce, I end up with 6y squared. Right? Integrate from -1 to 1. So I plug in the top limit of integration into the y. 20 times 1 plus 6 times 1 squared minus, now bottom limit of integration, 20 times -1 plus 6 times -1 squared. So I get 26 here minus, and then over here I have negative 20 plus 6, so that's negative 14. And so I end up with positive 40. So what that tells me is that the volume underneath this surface over this rectangle is 40 cubic units. Okay. Let's take a look at one more. Here we want to find the volume under the surface, z equals x, root 4 minus x squared over y, and over the rectangle R. Okay. Now, volume under the surface, that's exactly what this multivariate integration is good for, right? So if I want to find the volume under the surface, then I want to integrate over region R, over my rectangle, and I want to integrate my surface, which is z equals x root 4 minus x squared over y. I want to integrate it over the area of this rectangle, so dA. Okay, so let's briefly sketch what we're dealing with here. xy, r goes from 0 to cross 1e. What that means is this is the region of the x, this is the region of the y. These are intervals, okay? And then this means we're in 2 dimensions, okay? I'm looking at this along the first variable, the first dimension, and this is the range of the second variable or the second dimension, and I'm putting them together, okay? So x goes from 0 to 2, so there, and y goes from 1 to e. Now e is about, what, 2.71? So not quite 3. So 1, 2, and then e will be a little less than 3. So the region that we'll be looking at is this one right here. We are going to find the volume over this region. This is region R. Okay, we're going to find the volume of this surface over this region. Again, we just have the xy plane sketched out, right? You can imagine we're looking down the z-axis. The surface is hovering above this region somewhere. We want to know the volume between the xy plane and that surface. Okay? All right. So how do we actually do this? Well, we need to translate this from a single double integral to an iterated integral, 2 single integrals. Okay? Instead of a single double integral, 2 single integrals. So I'm going to integrate one variable at a time. Now the question is, do I integrate dx first or do I integrate dy first? So it actually doesn't matter, right? I could integrate this direction first and then this direction, or I could integrate this direction first and then this direction. It does exactly the same thing. Sometimes one direction will be easier than another to do first, but theoretically they should both give the same result. Okay. Now in this case, it really doesn't matter. Both variables are going to be about the same difficulty no matter which order I integrate them in. So let's integrate with respect to y first. Okay, so if I'm integrating with respect to y, my boundaries are from 1 to e. Okay, that's going to be the inner integral. I'll integrate with respect to y. Y will range from y equals 1 to y equals e. I'm going to hold x fixed. And then once I'm done with that, I need to integrate the other variable. So I'll integrate the x. Okay, the x ranges from 0 to 2. So x equals 0 to x equals 2. Okay, so now we do one integral at a time. I'm going to do this integral first. I'm going to treat x as a constant, which means I can treat all of this up here as a constant. So what's the antiderivative of some constant divided by y? Well, it's just constant comes along for the ride. And the integral of, say, 1 over y, that's going to be natural log of the absolute value of y. We're going to integrate that from 1 to e, from y equals 1 to y equals e. Okay, so notice this outer integral. I'm making sure I write it every time. I don't want to forget about it. Okay, do not forget about it. If you don't write this, it's wrong. Okay, that's not the same thing. Those are not equal. Okay, so even though it feels like it's just busy work to write that, do not write it. It's important that you write that outer integral every single time so that the equations stay the same, so that that equal sign is true and that we don't forget about it. Okay, so I want to evaluate this from y equals 1 to y equals e. I've got this constant in front, and let's plug in my limits of integration. Now both 1 and e are positive, so I could drop the absolute value, right? So I get natural log of e minus natural log of 1. Okay? So let's simplify. Both of these are ones that we should know, and if we don't know them, now is a great time to learn. Natural log of e is just 1. Natural log of 1 is 0, because we could think about it as e to the 0, natural log of e to the 0. And then you could bring down the exponent to the front. So I'm just going to get 1 there. So all of this is 1, and then 1 times x root 4 minus x squared is just x root 4 minus x squared. And we are done with the inner integral. So just a sanity check, our integrand at this point should no longer have that inner integral variable. If it does, we have done something wrong. And in this case, it doesn't, right? There are no y's left in my integrand. Once I get to that point, once I'm done with that inner integral, I should have no variables left from that inner integral. Now the only variables left should be the x. Okay? And that's great. We've got it so far. So what we've actually done so far, we held x constant, we integrated with respect to y. So we sliced it up like this. Okay, and for each slice, we integrated that y value. Okay, each slice gave us a single value. So now we've gotten rid of the y-axis. We only have the x-axis left. And each one of those slices translates to a point along this line. And now what we want to do is we want to integrate along this line. We integrated here. The down arrow probably isn't great. I probably should be an up arrow, but you understand. We integrated with respect to y. That kind of collapsed all those y values. You can kind of think of squishing this down, and pushing all of them into a single value. Okay, we squished it down into this, and now we're going to squish it this way so that we get one value when we're done. Okay, so now let's integrate with respect to x, squish it down that other way so we only have a single point when we're done. How do we integrate this? This is just your standard single variable integral. Again, this is a calculus 1 integration problem. There's no crazy tricks here, but we do need a u substitution. Specifically, my u should be 4 minus x squared. So the derivative of u with respect to x is negative 2x. I like to put all my x's on one side, everything else on the other side. So I'm going to move dx to the right and move the negative 2 to the left. So I end up with du over negative 2 on the left and x dx on the right. So that tells me that I can swap out 4 minus x squared, that part there, with a u. That's great. That's the nasty part that I wanted to get rid of. As long as I am able to find an x dx to swap out with d over negative 2. If I'm going to use variable u, I need to integrate with respect to u. And so I need a du. Okay. I do have an x here, so I can make that substitution. Okay. So x dx becomes du over negative 2. That negative 2 in the denominator, I'll pull out front. It's just a constant, so I can pull it out in front of the integral. And then square root of 4 minus x squared becomes square root of u. And then I need to change my limits of integration. These limits of integration are from x equals 0 to x equals 2. I no longer am using x. So let's swap them out for our new limits of integration in terms of u. Okay? So if I plug in x equals 0, I get 4. If I plug in x equals 2, I get 0. Okay? So the 4 should be where the u should be 4, where the x was 0. So that needs to be down here. Okay, I plugged in 0, got 4. And where the x was 2, where that was my upper limit, so now my new upper limit is 0. So make sure you get the order right. I'm going from 4 to 0. All right, square root of u is just u to the half power. So just a little power rule here. U to the half power, add 1 to your power. I get u to the 3 halves and divide by your new power. So dividing by 3 halves is the same as multiplying by 2/3. And I'm going to evaluate that from u equals 4 to u equals 0. Okay? Now 2/3 is just a constant, so I can pull it out, multiply it by the negative 1/2. I'll just get negative 1/3 once I multiply those together. And now let's plug in our limits of integration. Top limit always goes first, so 0 to the 3 halves power minus 4 to the 3 halves power. Okay, of course 0 to the 3 halves power is just 0. For 4 to the 3 halves power, I'm going to first deal with the half part of the power. That means square root. Square root of 4 is 2. And then the 3 part of the power, that's going to cube it. So half square root of 4 is 2, and then cube it, I get 8 with a negative in front. So negative 1/3 minus 8 is just 8/3. That is the volume of this surface over the rectangular region R. Okay. Now we've done this particular integration by first integrating with respect to y, and then integrating with respect to x. On your own, just as an exercise, double check that the order of integration doesn't matter. Okay, so if I swap the order of integration so that I integrate first with respect to x and then with respect to y, confirm that you get the same answer. So if I integrate first with respect to x, that would be from 1 to e, and then with respect to y, 0 to 2. Doesn't matter the order of integration. Go ahead and check. You will get the same answer, 8/3. Oh, wait. Sorry, my mistake. These limits are wrong, right? X goes from 0 to 2. Y goes from 1 to e. Okay. So we really have switched it. The x went on, if you put the x on the inside and you put the y on the outside, you will get the same result in this case. You can swap the order of integration. So go ahead and give that a try. Confirm that you get the same results.